What's up, guys? Welcome to a new series we're going to call Reverse Engineered, where we talk about all things engineering and engineering. And we just get geeky in front of the camera so that you guys can see what goes on in our crazy ass heads. Yeah. I think we're going to start with the differences in CFDs. What did we call this?
Not all CFDs created equal.
All right, so we're gonna call it Not All CFD is Created Equal, because guess what? We see it all the time on the internet that other people do CFD, and then what do we do differently? And is it all created equal? Well, we obviously don't think so, but we're gonna go into some of the bullet points as to why we don't think so, and let you guys be the judge at the end of the day. We've been doing this for almost a decade now. All right, so I'm gonna ask Matt, who is our current design engineer, CFD engineer, some questions that, you know, kind of prompt some answers that we'd like to see. So, Matt, how did you get into CFD?
So my first real world exposure to CFD was back in 2016 when I was an intern for a Paul Lucas, who some of you may be familiar with.
Hello, I'm Paul.
Yeah, so that's kind of when I first became aware of open foam and kind of started learning a little bit about how automotive CFD works and what's important, what to look for. And I've just kind of slowly been chipping away at learning CFD since then. Yeah, I would say Paul's very much a mentor in that regard.
Matt's relationship with Verus goes back to 2018, 19. It was before COVID. Yeah, and we were trying to set up our first server on site, and we pulled all-nighters, and Matt was messing around with Carol's race car, which is the first rendering that we kind of meshed, what would you call it, like a render of a car and CFD in Blender, and Matt kind of made that come to life, and then we posted it, and it was cool. Yeah. So that was like the first time I remember legitimately meeting Matt, and then we were pulling an all-nighter trying to make the server work.
Yeah, so CFD is the most straightforward way of thinking of it is our virtual wind tunnel. So we use it to sort of test and validate our products, to look at aerodynamic performance, lift, drag, balance.
It's used in damn near every industry. I've seen it used even in buildings. So they'll actually flow airflow through a damn city to see how airflow will react with buildings and all that type of stuff. So I would say architecture, land, anything on the land, anything in the air, anything even, you can use CFD for water or anything fluid. Ships. So any fluids, so ships, submarines probably, anything fan related, anything that moves.
Anything that spins, anything that interacts with a fluid, which includes air, any gas.
Probably in the medical industry.
It's in the medical industry. They do CFD on like arteries and different, looking at
things inside your body.
Yeah, looking at what are those aneurysms? I think they do modeling with CFD for that kind of stuff.
It's basically a tool to allow you to visualize fluid flow that you would otherwise be guessing at. So it allows us to simulate any type of fluid flow, and people use it in every industry. I would almost guarantee it. I bet fast food uses it somehow.
Yeah.
Maybe for those dispensing machines, I don't know.
I think that's why McDonald's
I hate my life.
McDonald's McFlurry machines are always broken. Probably not enough CFD.
Probably not. So as we have grown as a company, we've been doing this for a decade. We've seen a lot of other companies do CFD and try to, I'm not gonna say emulate, but maybe follow in our footsteps in some way. We weren't the first though. We're not the last, that's for damn sure. But we do believe that we've gone about it in the right way, and there's other people that haven't gone about it in the right way. So one of the first things that is an easy telltale sign is if you're using SolidWorks. SolidWorks is a software that is used for engineering, and while a lot of companies use it, we've found that it really does lack in the ability to design things complex as well as flow fluid through it. So Matt, maybe you can expand on some of the issues while using SolidWorks versus what we do internally.
Yeah, so SolidWorks is obviously the go-to for like small, medium-sized companies for design. When it comes to CFD, it has a lot of shortcomings. I would say the largest issues are just in control, what you have control over and what you have access to in the setup of cases. It's more limited when it comes to meshing. It's more limited when it comes to turbulence modeling. It seems to me like it's set up to be a very quick and easy tool that someone with limited background can set something up and run it and maybe get like a visual on sort of the gist of what's going on, but I don't know that I would trust it for anything beyond that.
Yeah. As soon as you start trying to discern any of that data from there, you're probably potentially going down the wrong path at the end of the day, because the mesh and the turbulence model actually really do matter, and all that stuff, it matters.
Yeah, I would say meshing probably matters almost more than anything else, and I haven't played with SolidWorks CFD a lot, but I think it's mesh refinement and adjustability leaves a lot to be desired. And then when you're going from one case to the next, one platform to the next, it's just not a very streamlined process.
So what we have noticed as well is car scans. How are people obtaining their data and actually running cars through CFD?
For us, step one is to actually do a 3D scan of the entire car, or most of the time we'll do a complete rear bumper, front bumper, and a little bit more than half of the car. Anything that's not symmetrical gets scanned, so usually the underbodies get fully scanned because they're often asymmetrical. But that half car plus some of the wraparound of the front and rear give enough data to establish a center line and mirror it. Obviously, if you want to be really specific, there's probably going to be differences from left to right, but we kind of have to draw a line in the sand somewhere. So that's kind of how we do it. That scan then gets solidified into a CAD model.
Generally speaking, our CAD models are less than 0.5, 0.7 millimeter difference from
Yeah,
the scan data.
It's been a while since
So-
I looked at one, but
And we could do a whole nother freaking video on scan data versus solid models, but ultimately a scan data is a bunch of triangles, well actually points, it's point cloud, and then when Matt says CAD, that actually means it's a geometric model. So when you take a point cloud and then you try to put geometry to it, it's not actually a parametric model. They're like, CAD is parametric, point cloud is not, so you're gonna have deviations no matter what you do, and the closer you get, the more time consuming, but what I'm trying to get at is we get pretty damn close.
yeah, another thing that we tend to see a lot too is it looks like people are using models that they've purchased online. Often these models are created, they're very detailed, nice models, but they're usually created more for like visualization, and they're often gaming or just like product visualization, that kind of stuff. They're often modeled from like reference images. Like someone has a bunch of reference images of a car, and they'll kind of line them up in a software and model the car from pictures. But we have purchased some of these models and looked at them, and when you overlay them
Very early on. Let's be honest,
yeah.
We don't do it anymore.
I've taken one of those models and overlaid it with scan data, and it's just not it. Yeah, to look at it, it looks just like the car. You'd be like, wow, that's a whatever. But if you overlay the scan data, the wing profile is not going to be accurate. The wing might not be in the right location. Proportions are just all slightly off. Even like the entire width or length of the vehicle might be a little bit off. It's just a really good visual representation, but it's not accurate for. Yeah, so they'll take like you'll get a picture that's like a front view, side view, top view, maybe some different views. Ideally, you'll get all of these photos from like one photo shoot. That's like one camera, ideally one focal length, and there's techniques you can use to try to line them up so that this point on this image matches this point on the same point on a different image, and get it all kind of lined up. And then you're essentially tracing. It's an impressive skill for sure, but it's not a 3D scan.
So after we've got the car scanned and it's fairly accurate, we throw it into, well, we can throw it into CFD. And what I mean by that is we actually output it from our CAD system and we throw mesh onto it, and then we make sure that the mesh is actually good.
The mesh is, I guess you can look at it as you have a computational domain, and that's our virtual wind tunnel. So it's like, I don't know, maybe it's 10 times longer than the length of the vehicle, and it's several times wider and taller, and that's to avoid issues with what in wind tunnel parlance is blockage ratio.
Blockage ratio basically means that you're not having the walls interfere with what the car is doing. You want enough area so that the vehicle is not interfering. The airflow off the vehicle and around the vehicle is not interfering with the walls, which is part of the issue with some of the wind tunnel testing we've seen online. Continue, Matt, sorry.
Yeah, so that, the blockage ratio is kind of like the area of the vehicle compared to the area of the wind tunnel. But so you end up with this big 3D like rectangular prism, and it's full of cells, these mesh cells. So you can kind of look at that volume as a rectangle minus the car, and that big volume gets filled in with a mesh, and they're all points at which the CFD equations that the computer is solving do calculations at each of these points. So some of the things to take into consideration are the actual cell size, the number of cells you have in a mesh. There's a bunch of different things you can do or look at to check your mesh quality. There's cell aspect ratio, orthogonality, skewness. These are all different. Like I know when I mesh a case, I get an output report that lists all of these values, and I can look to see if there's anything that looks strange or looks like it could be a cause for concern. The actual number of cells that you have in a mesh, you can do mesh sensitivity studies where you essentially do a coarse mesh and run the case and iteratively increase your mesh count and keep running the case over and over again, and you might start to see your results change a lot from a small mesh to a medium mesh. But as you refine the mesh more and more, that the values that you're getting kind of should start to plateau at some point. And at that point, you know that the size of your mesh isn't really changing the impact on your results. And it kind of takes that variable out a little bit.
At this point, we've got enough data from various cases. We know roughly how many cell counts we need for a high downforce system or vehicle, how much we need for an OEM car to basically improve the performance of the computer and still get the data we need. So we have it pretty scienced out at this point. One of the questions I would ask other people is, have they ran mesh sensitivity studies? They'll probably say yes, but it's one of the things that we've done. I don't know if other people do it. It's definitely something that needs to be done.
Yeah, another thing that we've done in the past as well is wind tunnel correlation. So that computational domain actually becomes a 3D model of the wind tunnel you're testing in. And you can kind of refine some of your meshing and turbulence model parameters to see how close of a match you're getting to the wind tunnel.
We did that quite a few years ago. We were less than 2% off, which we were pretty happy with, because at the end of the day, an actual wind tunnel is a simulation as well. And even then, they can't ensure that everything is perfect. And just like CFD, we can't ensure that everything is representative of real world, but like that correlation of being less than 2%, we were pretty happy with that.
They're all tools.
Yeah.
And different tools work in different situations, and as long as you're using them properly, you can get meaningful results. So it's no different than you see a lot of discussion about dynos on the internet. Like which dyno is accurate? What does accurate even mean? Different dynos are going to give you different results, but if you have a good feel for your setup and understand the results you're getting, you can use them to tune a car. It doesn't really matter what. To some extent, it doesn't matter what tool you're using. Obviously, we're sort of saying that SolidWorks probably isn't it, but
Yeah.
if you're using a proper professional analysis package, you can probably get meaningful results if you know how to use it properly. So almost all of the cases that we do are RANS cases. Reynolds, averaged, Navier-Stokes. There's a bunch of different sort of categories of CFD, if you will, DES, LES, RANS. RANS is less computationally intensive than some of the other options. It also tends to under-predict lift and over-predict drag, but if you know that, you can make the right decisions to work with it.
And we've actually seen that. That's what our wind tunnel actually, our wing wind tunnel testing actually showed that as well.
Yeah.
There's a lot of people that do CFD and then they never correlate it to the wind tunnel. I'm not saying that that's necessarily the right way or the only way to do it. Before we went to the wind tunnel, we did a lot of other things. So we actually ran a drive air model. We ran a Perrin LMP model. We also did the Ahmed body. And then we did known wing profiles. And then that's how initially we got our CFD correlation to match at least other published known valued vehicles and objects. So this is all like very heavily researched bodies. And honestly, they're like, the Ahmed is really boring. The Drive Air is a little bit more representative of like a German car. And then the Perrin LMP is a high downforce car that they publish values for. But basically there was values, and then we made sure that our values were similar, if not the same, to those values.
Yeah, they're sort of like industry standard cases that have an accepted set of results based on CFD, wind tunnel, all this different testing, and it's something that you can sort of use to calibrate your work.
We actually did those correlation works to make sure that each time our data was correct, because that's what we do. We're engineers, we're boring. All right, so what is Y+? We've heard the term thrown out there. We definitely throw it out there. If you don't hear other people throwing it out there, what does Y+ mean? Why does it matter?
Yeah, so Y+ is another parameter that you can use to check the quality. It can check if your mesh is the correct size, if your cell height is the correct size. It's a non-dimensionalized number, and essentially what you're doing is, if you're using wall functions in your turbulence model, which is some of this empirical data that's used to describe the behavior of flow really close to the surface of an object. So you've got air cruising along a surface. Up here, you've got your nominal free stream velocity. Because of skin friction, the closer you actually get to touching the surface, the slower your velocity will get. And at the surface, because of friction, it's actually zero. So you get this kind of this curve that is called the velocity profile. Wall functions are used to calculate what's happening in that sort of lower portion that's in the boundary layer that's really close to the surface. You can not use wall functions, and then you're going to want to have, it's all dependent on your turbulence model that you're using, but say you're going to want to have a Y+ value of less than 1, which means that you have a whole bunch of cells stacked up really close to the surface, and you're actually fully resolving and calculating the behavior in that boundary layer. If you're using wall functions, you might want to be in like the 30 to 300 Y+ range, and that allows you to, it massively decreases your mesh sizes, and it still gives accurate results. You can decrease your mesh size while still maintaining a certain degree of accuracy, but if you're not in the correct Y+ range for what you're trying to do, you're not going to get good results. And that Y plus value is, it's dependent on like where on the vehicle you're looking at as well. So it's not just like it's 5 or it's 26. You kind of have to look at your mesh as a whole and make sure that your mesh refinement is giving you Y plus values that make sense for what you're trying to do.
Something else that we do on our CFD analysis is we spin the tires, and this allows us to improve our accuracy.
Yeah, so like if you're going 100 miles an hour, your tires are spinning extremely fast, and that just causes a lot of disturbance to the air moving around them. You get what's called tire squirt, which is kind of, you look at as the tire's rolling down onto the surface of the road, what happens to that air that is existing in that space that suddenly needs to be elsewhere. So it really depends on what specific thing you're looking at, how important it is. But if you're working on anything that has to do with the like a splitter, diffuser, underbody behavior, that rotating tire is going to have a pretty large impact. So it's important to be aware of and take into account.
So something else that we do on our CFD is we add a little bit of yaw. And that's because, first off, yaw means the vehicle is going through the air, or air is actually flowing over the vehicle at a slight angle, not directly in front of it. So no yaw would be airflow flowing directly longitudinally on a vehicle. It's very unlikely that ever happens in real life because 1, the car turns in corners, and then 2, crosswinds. So we don't want to analyze a vehicle in a perfect scenario, which is very, very unlikely for it to happen. So we add a little bit of yaw, which generally does hurt our results, but we also ensure that nothing funky is happening with results. Matt, would you like to expand on that anymore?
Yeah, so a good example of something that yaw might impact would be like one of those really streamlined looking roof antennas. If you're only ever flowing air straight over that, it might be very easy for airflow to just kind of laminarly cruise around it and reattach behind it, and it's kind of like it's not even really there. But as soon as you look at that roof antenna at like half a degree of yaw, it has a lot more frontal area, and it can have a much greater impact on the flow field around the car. So doing yaw is it's computationally more expensive. We have to run a whole car. A lot of people will actually cut the car down the center line and only actually run half of the car in CFD, and then you can essentially just mirror the results.
Full disclosure, we did that early on too.
Yeah, and there's nothing wrong with that as well. It's just another technique, another tool.
Hey, and a little hint to everyone, we're probably, as we grow, we'll probably do cooler and cooler stuff too. So like this is just where we're at right now. As you can see, we started down here, we continue to like go up. Well, we're probably gonna continue to go up. That's just the life of business.
Yeah, and it's kind of early on, we included a lot less underbody detail. We included a lot less suspension detail.
As we've gotten better, we continue to refine our techniques and get closer and closer to what we expect or see in the real world.
Yeah.
And that's just what that's just kind of what we do as we improve ourselves and improve our products.
Yeah. Engine bay and heat exchanger details are something in the early days, that's not something that we looked at. It's not something we look at for every platform, but we're doing it more and more. And running 2 cases, everything equal, but one has some engine bay model with heat exchangers in it, and one does not. It's a very significant difference between what you'll see. Yeah, you can still learn some things about the behavior of a vehicle. You can still design some parts if you don't model that. But I don't know, something that I get really excited about is when we design an aero package for like the M2, and we put it on Jackie's car and say, Jackie, you're probably gonna want the rear wing at around 4 or 5 degrees, knowing what he likes, and he comes back and says like, yep, ended up at 4 or 5 degrees. But yeah, so it's I don't know, to me it's really satisfying to say like, here's the package, this is what it's going to do, this is probably how you're going to want it set up, and to have that from his feedback be like, yeah, that was pretty much what I wanted. So makes me feel like I'm doing something right. Makes me feel like the kind of the IP, this like vast resource of knowledge that Verus has built up is heading us in a good direction, because that's kind of what's guiding me in my work. And yeah, that's a cool feeling. So we'll probably keep adding more detail, look for more ways to improve our processes, and keep on going.
And something with that M2 aero package that we hadn't done before. So we had 5 heat exchangers modeled on the M2, which wasn't a first for us, but it was a first where we had an oil cooler that was laying flat on the top of what we have is the splitter basically. And we had airflow dumping out underneath the car. And Matt basically had to figure out how to make this garbage airflow out the bottom of the splitter actually function well. So we ended up creating a bunch of stuff. But what I'm trying to get at is, if we didn't model those heat exchangers and we didn't actually care about airflow coming out of the heat exchangers, that analysis would have been totally null. We saw a massive decrease in front downforce because of that oil cooler dumping air straight down. And then we tried so many different iterations, and we ended up with a duct to actually really get back, like 85% of the front downforce or something. Yeah. But I guess what I'm just trying to get at is, if we didn't do that type of stuff, we wouldn't learn ahead of time. Jackie probably would have gone out, hated it because he would have no front grip, and then he would have punched us in the face.
Yeah, the M2 splitter is actually quite large. It's probably more similar to like our high downforce splitter for the Supra, and it was kind of necessary because that oil cooler had such a large impact that we realized we were going to have to go a little bit more extreme than we normally would have. But yeah, it was cool to learn that.
Thanks for watching this episode of Reverse Engineered. Be sure to like and subscribe. And if you have any comments below, we love hearing them. If you have ideas for what you might want to see on this series, Alex is always interested and willing to listen to that and potentially make it a video. Until next time.